Hey, Katie.
Hey, Ben.
So, in this episode, let's take a little bit of time to take a huge step back and look at artificial intelligence with a lot more perspective than we usually do. A lot of times, our episodes are very much about a particular method or something.
That's right, but there's also a lot of ground that we end up not covering as a result, and there's some very interesting work that's going on not just in specific fields, but in trying to tie together fields that look like they have nothing in common, seeing if there are ways that they can be combined in a way.
So, this is your meta episode of Linear Digressions.
So the inspiration for this episode was actually a listener, or maybe even a couple listeners. So Laskar Anderson and James Kelly, you both had a couple suggestions about things like the Wolfram language and cognitive AI and the master algorithm. So thank you so much for sending those in. It's been really fun learning about them. Maybe the place to start is with what I said, the master algorithm. This is actually the name of a book that was written by a computer scientist named Pedro Domingos. And what he decided to do was to take a step back from all of the work that's going on in artificial intelligence and to try to categorize it into one of just a few buckets and see what are the different approaches that each of these different buckets are taking and what are their strengths and weaknesses.
And I just want to briefly mention that talk by Pedro Domingo, it's up on YouTube. It is fascinating, and he does a great job of kind of summarizing a lot of what's going on in the space, which is what we're going to kind of try to summarize his summary right now. But if you're interested in this episode and you want to learn more, that's a wonderful talk to watch.
I agree. I really enjoyed watching it. So the high-level view of what he's trying to do is he has 5 different categories of artificial intelligence based on sort of the philosophy of how they're trying to solve the problems and also somewhat the history of artificial intelligence. And he's asking the question of, are there ways that these methods, which are each very strong in their own domain, is there a way that they can be combined to be more than the sum of their parts, to be perhaps a potential route to true artificial intelligence? In the way that we think of it, kind of blue sky is what artificial intelligence means. So his category, he has 5 of them. First is the symbolists. So these are people who have a background or a paradigm of using things like logic and philosophy, and they work with inverse deduction. So this was a field that had a lot of early action in it. So in the 60s, 70s, 80s especially, this was where a lot of the work was. And it's things that kind of follow the recipe of Socrates is a man, all men are mortal, therefore Socrates is mortal. That's a logical statement, and that by programming the rules of logic into a computer and then making manipulations within those rules or combining those rules, that you can come up with something that can go from sort of point A to point B via this logical chain.
Mm-hmm. So you could take A and B, therefore C, or I know A and I know C, so I can infer B.
Yeah, it's stuff like that. And this had some early successes. There was a program, it's kind of funny actually. It was a program that was designed to have an internal simulation of you stacking blocks on a table. And so you would send it commands in natural language, like put the red box on top of the large blue box. And then it's in its internal representation, it actually has an idea of there's this little table and there's all these blocks and they have different colors and shapes and sizes, and it will move them around sort of in its head. There's no physical blocks. But then you can ask questions like, maybe you say, put the red box on top of the blue box, put the green pyramid on top of the red box. What is the green pyramid on top of? And it would say, well, it's on top of the red box and it's also on top of the blue box because the red box is underneath the blue box. And so they were able to get some fairly fun little results where it can keep track of all of these things, and it was getting the relationships right. But they weren't ever able to get it to like do anything useful. It was all just like a block building program, and any attempts to get it into something that was a little bit more real world, those rules just ended up being a little bit brittle.
Right. Yeah, the real world is a little bit fuzzier and much more complex.
Yeah, so the symbolists, it's still a very interesting paradigm, and I think that there's a lot of respect for that way of thinking in general, but a lot of the heat and the noise in artificial intelligence has now transferred over to the second group, which is the connectionists. So these are the neural net guys, basically, is the way that I think about this.
Mm-hmm. Yeah.
So neural nets are having a lot of success right now with things like image recognition, speech recognition.
We've done a lot of our episodes about the connectionists, basically.
Yeah, they're really having a moment. I think there are also, clear places where neural nets have some disadvantages. So one example is a neural net is kind of a data processing algorithm. It's not really inherently a data storage algorithm.
Yeah, it's stateless.
Yeah, so if you want to have something like a whole database of facts about the world that your neural net can draw on when it needs to draw a conclusion about, say, like a case that it hasn't seen before, that isn't really built into the neural net algorithm, that it has a way to do that sort of information retrieval. So that's an example of something that, you could maybe get that round peg to fit into a square hole if you really wanted to, but neural nets are, if you wanted to have a neural net that was a full representation of like the way a human brain works, it would be maybe pretty good at the processing aspect of the human brain, but not quite so much at the memory aspect of it.
Just because that paradigm doesn't have storage baked in. It doesn't have like looking into a database of facts or something like that.
Yeah, another thing about neural nets is that there isn't anything built in that allows you to just randomly add some noise to the neural net, usually, to change things and see if it gets better. And what I'm thinking about when I say that is evolution. So evolution is a way of transmitting information from generation to generation via a genome, and that your genetic material is always getting recombined and mutated. And
that's the crux of it, is the random noise that's entered into the system. If you don't have that random noise and those random mutations, then you can't accidentally stumble across an organism or a program which is actually somehow better suited to what it's trying to do.
Well, and there's also evolutionary natural selection that's going on too. So stuff that works well, has a way of sort of bubbling to the top and getting propagated, while the stuff that isn't working as well gets naturally trimmed away by the process of evolution. So evolutionaries, this is the third paradigm, they come generally from evolutionary biology and use the rules of genetic programming to think about just a totally different way of transmitting and curating information.
And you can see kind of a basic version of the work that they're doing if you search for something like watch this creature learn to walk or something like that. There are these programs that you can find on the internet that are actually running in your browser that are genetic algorithms. And so it'll be a representation of like a dinosaur creature and it's trying to walk. And you watch as multiple of these, multiple mutations of the original creature kind of race each other. And then whichever gets the furthest, or maybe the top two that get the furthest, are the ones that make it to the next round. And you can see that evolution happening. It's really kind of amazing to actually see it happen and see it work. It's something that you can kind of intuitively understand just by watching it.
Yeah, very cool stuff. So the fourth one, this is near and dear to my heart. These are the Bayesians, mostly people with a background in statistics, and they use things like probabilistic inference to do their work. So this is things like, I'm going to look at many examples of something happening in the world, and I'm going to analyze them within a statistical framework and say probabilistically what are the things that are most likely to be happening in any given point. If I'm doing controls properly and I have sort of the right experimental setup, I can also do inference. So I can start to say things about, is A causing B? Well, if A is causing B and I change A, what do I expect to have happen to B? So this is a very powerful paradigm that gets used a lot in data science. But it's not something that works particularly well for maybe, for example, speech recognition. Like the connectionists seem to have it in speech recognition. There were some statistics-based machine translation approaches that bore some fruit in the early 80s, but they're just being blown out of the water right now by the connectionists.
Yeah. Mm-hmm. So potentially very powerful for certain situations, but not as fruitful with other ones.
Yeah, yeah. Like all these things, right? And then the last one, these are called the analogizers. This has a background from psychology. Maybe this is where you get some of the cognitive people as well. So, and approaches that they use are things like kernel machines and support vector machines. And this is the one that I'm the least familiar with, honestly. But it seems like kind of the idea that if you learn something in one domain, are there ways that you can analogize that to another domain, and you can do things like it sets you up for more elegant transfer learning of not having to learn every rule or every fact individually, but that you can start to make generalizations based on the more limited examples that you've seen.
So this seems kind of frustrating because we've got these 5 fundamentally different paradigms. All of them are quite successful in certain ways, moderately successful in other ways, and unsuccessful in even other ways. And it seems like if we could only just kind of like smush them together, like in the commercials that you see for smoothies where there's like an apple and a banana and they smash into each other and a smoothie comes out. Like I wish we could do that with these, because if there was some way to combine them together where you could get all of the pros of each of them without all of the cons, then potentially we could, go even a lot farther in a lot of these different fields.
Yeah, and I think that's the value of sometimes taking a deep breath and looking up a little bit, because you can spend easily an entire career just in one of these fields, making very great progress. And there are a lot of people who I have huge amounts of respect for who've done just that and have moved them very, very far. But I think there's also starting to be more and more of an understanding that each one of these fields has its own limitations. By now, we understand them well enough. We've been studying them long enough that I think we're starting to understand that where the limits are for each of them. And so as a result, people like Pedro Domingos are looking at this and starting to think about what it might mean to combine them. And if there are ways that you can combine them, and what the strengths of the system that you could get out of that would be. If this would look like maybe you take a neural net and you feed it into a genetic algorithm, like, is that what we're talking about? Is there some kind of third algorithm that is structured completely differently from each of them, but has the same properties of both of them? I mean, it's a sort of wide open topic right now, precisely because there's been so much effort, I think, developing each one of these individually. But it's starting to get pretty interesting, and there are a lot of very smart people who are working on this. I read a really good article in the MIT Technology Review called "Can This Man Make AI More Human?" And it's about one of these researchers who's specifically thinking about things like cognitive science and what are some of the indications that we can get from watching human learning that can tell us what a more powerful machine learning might look like. So, for example, what machine learning kind of looks like right now is if you imagine a machine translation system, right? Or a speech generation system. A speech generation system, it talks like an adult, sort of an awkward adult, and one who sometimes strings together phrases that don't make a whole lot of sense or they're not very elegant, but it doesn't talk like a child. And that's very interesting, because another way that you could think of this field progressing is that you could make a speech generation system that starts out talking like a baby, and then as it becomes more advanced, it just starts talking more and more like an adult. And that would be another sort of intuitive way that this could be going. And so he's starting to ask questions like, well, why did it end up going this way instead of that way? And are there generalizations that we can make from the way that humans learn, like especially when you think about children as they learn something, that can inform the way that we're combining some of these different systems? Because humans have many different systems and many different ways of synthesizing information and moving it around from one place to another. And is there inspiration we can draw from that when we're trying to reconcile several different approaches? And then another interesting example of this is some of the work that Stephen Wolfram does.
Oh, yeah. The guy, Wolfram Alpha.
Yeah, Wolfram Alpha, Wolfram Mathematica, which I got to know very well when I was working in physics. Mathematica is a really interesting program that actually does things like it can do mathematical manipulations. Like we would always use it to take hard integrals. And it does it analytically. It doesn't do it numerically. So it actually sort of understands the rules of math and can do mathematical manipulations within the software, which is really, really interesting.
That is really cool.
And Stephen Wolfram has been working on this thing called Wolfram language. And it's kind of interesting. I don't know that it has quite as much of an uptake as he was saying it would. But the idea is that there's lots of knowledge that's already pre-programmed into the software. So it knows things like the rules of math, the rules of physics. It also knows a lot of facts about the world. It has a lot of domain knowledge. So it knows things like, what are the countries in the world? And what does it mean that a country has a population? And what are the rivers? And how are they related to the rivers, in the sense that like rivers go through countries. And so then you can start to use rules to sort of move your way around this knowledge graph. And the knowledge graph then becomes part of the algorithm, and the algorithm is contained within the knowledge graph. And so it's a very interesting idea. Like I said, I don't know that it's had as much pickup as he was saying that it would, but it's certainly more evidence of some very smart people who are trying to take a step up and do more meta-level artificial intelligence than some of the stuff we've seen so far.
So what were the resources that we were talking about?
Right. So the one that I suggested, the MIT Technology Review article, I thought this was a very interesting take on cognitive AI. It was entitled, "Can This Man Make AI More Human?" So you can find that just by Googling.
And the YouTube video that we're talking about by Pedro Domingos is called The Master Algorithm. You could just search for his name and The Master Algorithm, and it's one of the talks at Google that Google put on. And I really love this one. It's an hour long. It's quite long, but he goes into a lot more detail, and it's very accessible. So if you're relatively new to this field, like I am, you'll actually find that it's quite accessible, and that he gives a lot of good examples of all of these different things. So definitely something that's worth an hour of your time if you're interested in learning more. Linear Digressions is a Creative Commons endeavor, which means you can share or use it any way you like. Just tell them we said hi. To find out more about this or any other episode of Linear Digressions, go to lineardigressions.com. And if you like this podcast, go ahead and leave us a review on iTunes so other people get to listen to this content too. You can always get in touch with either of us. Our emails are ben@lineardigressions.com and katie@lineardigressions.com in case you have comments or suggestions for future shows. You can tweet us at lindigressions. Thank you for joining us, and we'll see you next time.